All right, today we begin mathematical induction. A lot. Okay, I will be, I'll tell you this. Mathematical induction is one of the more difficult forms of proof. Thank you for fixing that. But, and I'll be honest with you, I don't think it should be taught now. I think it should be taught after you've learned some of the other methods of proof, because we don't have a lot of time. Now, how it works. Imagine a ladder. Now, if we're trying, what mathematical induction tries to do is it tries to prove things that are infinite for the most part. Trying to prove that something always is true, no matter what. And the way you can kind of think about it is the concept of a ladder. You prove, in order to prove that you can climb up this ladder, you first step on the first rung. And if the first rung holds, wonderful. Then you say, I can take a step. And I climb one step up the ladder. And if you can successfully climb up one step of the ladder, you can induce that you could climb up any step of the ladder and go all the way up to the top. Okay? So there's an assumption that has to be made. You have to assume that this next step will be just like the one before it. Okay? So the best way I can kind of attempt to show you this is to actually do one. Okay? Now prove that if I do, let's see if I can get a nice one first. Let's get a nice simple one to begin with. Where's the, right. Up to, say, n. Okay? This is fine. Now here we are saying 1 plus 2 plus 3 plus 4 plus 5 plus 6, and so on and so on and so on and so on. What kind of a sequence is this? Series is this, sorry. It's a arithmetic sequence, okay, that I'm adding up, so it's an arithmetic series. And this is equal to the formula that we know, that we just showed a minute before, right? N over 2 1, which is my first step, plus n, which is my last step, right? Okay. So we first show, the first step that we do is what's called the base case. The base case is, for all intents and purposes, the first rung on the ladder. Show that it holds for a very simple example, usually the first example, the first number. So, now, actually, we're going to change our variable here. J. Then, in this case, actually, do we need to change it now? I don't think we need to change it right now. No, we don't need to change it now. We can keep it as J, as I. All right, then 1 plus 1 1/2 times 2, which is 1, and 1 equals 1, right? You could say then the sum of I equaling 1 to 1 is this. Right? Does that make sense? And if you wanted to, you could do others, but the fact of the matter is the first example worked. Okay? It actually is a true statement, at least for the first number. Now what we're going to do is we're going to assume that the original statement is true. Okay? And we're going to prove that the next step is also true. Okay? So, now there's a little bit of verbiage going on in here, and you got to have some, actual sentences thrown in your proof. This isn't just starting with numbers and ending with numbers. No, this is writing intensive. Now, this actually needs to go into your proof. You have to have like some verbiage in there. As long as you have all the important pieces in there, then it'll be acceptable. So we assume that the original statement was true for some I all the way up to j being some rung of the ladder. Okay? And we're going to prove that the next step also holds. And if that's true, if you can say that the next step holds, you can say that it holds for everything. Yes? Because I can't assume that it's true for all I. That's what I'm trying to prove. Yes. J is one of the rungs of the ladder. And I'm going to prove that the J plus 1 case holds. Okay? I can't say that I assume it's true for all I. Because if I assume it's true for all I, then I don't need to prove anything because I've already said that the statement is true. I'm assuming it's true up to J. That's it. I'm not saying anything about any other number, except I know it's true for the first one, and I'm going to assume it's true up to J. J is some integer, J. That's all you know. It's an integer. Got it. All right. And we're trying to prove because if I say that I can stand on step J, and I can go from step J to J plus 1, that means I can step anywhere along this ladder, and I can climb the whole way up. Now, this is important because you need to know what your target actually looks like. Because if you don't know what your target looks like, you might just walk right on past it or not even, or go off onto the wrong direction and God help you. So that would be and this goes up to n plus 1. No, just n. And now this is j plus 1 all over 2. My first step is 1. My last step is j plus 1, because that's where I'm going. All right. Yeah, and I do go one more up, right? Because it was true all the way up to j. But it needs to be true all the way up to the next step, okay? So we start with the assumption. And the assumption said wait, was it n or was it 1? Yeah. Yeah, it's up to the maximum number of steps, right? Sorry. Clear it up. Because it goes all the way up to n plus 1, so now this is n plus 1, right? Because n is the number of steps. Sorry. This is a difficult one to go through, I know. It's painful for you, it's painful for me. And this was, the sum of this was n plus 1. All right, so this was the original assumption. You assumed that that was true because we proved it for the first step. Now, here's where some of the magic has to come. We have to figure out how to turn this left-hand side and this right-hand side into this and that. All right. Well, let's look at this left-hand side right here first. That thing goes 1, 2, 3, 4, 5, 6, all the way up to j, right? Sorry, all the way up to n. N was the max number, and then n plus 1. So if we look at this really closely, this is that's this upper one, right? That's what he looks like. This is what you're starting with. So how am I going to go from one to the next? What do I have to do to it? Add what? Add n plus 1. If I add n plus 1 to that left-hand summation right here, I will get that. Because that just means I'm adding another number to it, yeah.
It only moves by 1, and n is like the max number, then why would you? Because that's basically 2n plus 1.
What do you mean?
On the 1 plus 2 plus 3 plus 4, you're adding 1 each time.
Right.
So you're adding another n.
No, I'm adding one more. So like if n was 100, okay? This thing would be 1 all the way, 1 plus 2 plus 3 all the way up to 100. This one would be 1 plus 2 plus 3 all the way up to 101, right? Where? Come up here and point to it, because I don't know what you're talking about.
So like,
Yeah.
This is 100 plus 100 plus 1.
Yeah, 101.
So that's 100 plus 101.
Right. No, no, no. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. This is a summation all the way up to 100. I'm not saying this is 100. I'm saying that I mean, in fact, I can say it's 5,050. Remember? No, because because the summation went to 100. I need to add the next number, which is 101. Okay? Do we see how we can add 101 and change the notation? Yes? Good. This is probably going to, unfortunately, be a well-watched video. So, I'm adding it to the left-hand side. If I'm adding it to the left, I had better add it to the right. So this becomes, yay, we have our left-hand side. That's what we wanted the left-hand side to look like. That was the left-hand side of my target. Now we need to make sure that the right-hand side of my target looks like my objective. The right-hand side of all this math turns into what I really want. What I really want is this. That. Because I'm, yeah, I used to go to n, now I'm going all the way up to n plus 1. Ooh, I have to maintain equality. Then you have a problem. Then you might not be able to prove it. But I mean, all of the proofs that I'm going to give you are things that you can prove. So the question is how do you manipulate what you have to what you want? And willy-nilly change something without making the appropriate change to the other side of the equation. Okay? So now we got to manipulate this right-hand side a little bit. Okay? So let's get a common denominator. And maybe this would look better. Right? And now, let's see if we can continue to turn this thing into what we're looking for. Let's do a little algebra. And we can see that this is n squared plus n plus 2n plus 2 all over 2. And we're getting closer to what we really wanted, right? Because remember, what we really wanted was a whole big page. what we really wanted in the beginning of all of this was this. And if you look at that, you can see that that's n plus 1 times n plus 2 over 2. And we're getting close to it. Let's see if I can do this. Yeah, it's big, but let me see if I can make it a little bit better. So that's what we were trying to prove. So we added a term to both sides. And then we have to do some algebra to manipulate it into the form that we want. And now we clean it up. Yeah. I don't understand your question.
Like, how did you get the thing in the parentheses? I think it's from the second to last up to the last.
From here to there? Come on, guys. There's some steps that I should assume you should be able to do. And this is one of them. Because I have the commutative property of multiplication, right? I can do that. Okay? We all agree. Good. Because 2 is equal to 1 plus 1. Because I have the commutative property of addition. Because I have the associative property of addition. Because division by 2 is multiplication by a half. Do we see now? Good. Now, we have to finish this up, which was the desired form. So by the principle of mathematical induction, and I'll leave it at that, the principle of mathematical induction. For all I elements of the positive integers. That. the positive integers, not just the integers, because we didn't attempt to prove it for the negative integers. And a summation going in reverse can be rearranged to be one going in the positive direction, if we needed to. There's no need to do it for the negatives. Okay, let's try another. Ooh. That was a beast. It's going to be interesting when that gets printed to a PDF. Moving on. Okay. So let's attempt the base case. What's my base case have to be? 1? Well, if it's 1, then 2 is less than 1 factorial, which is false, right? 4, because that's the smallest one that we're trying to prove. The first step in this is 4, okay? So 16 is less than 4 times 3 times 2 times 1, right? So 16 is less than 24. Oops. So the base case holds. Now we make an assumption. We assume that it holds for all n something. So it works for every number, every integer up to j. And now we need to prove that it's true for the j plus 1 case. Now the j plus 1 case would be so every place there was an n, I replaced it with a j because a j is something up to n. We don't know. It's not n all the way, but it's true. And we are looking for the plus 1 case, which is the next one down the line. Now, let's try to figure out how we can turn the left-hand side and the right-hand side into those two things. The left-hand side could become my target if I multiplied it by 2, right? What do I need to multiply the right-hand side by? Remember what j and j plus 1 are. J and j plus 1 factorial are. So this is 1 times 2 times 3 times 4 all the way up to j minus 1 times j, right? It's multiplying every number all the way on up to j, right? And then this factorial here, this is 1 times 2 times 3 times 4 all the way up to j minus 1 times j plus 1. Say it again. Okay, yeah, multiplying this factorial by j plus 1 will give me my goal. Okay? But I want to multiply this by 2, and I want to multiply this by j plus 1. Is it legitimate? Can I do that? If multiplying by 2 on one side and then multiplying by j plus 1 on the other side, will the original statement still be true? Will it still be smaller than the right-hand side? Will the left hand still be smaller? Well, what's j? What's the smallest that j could be? So multiplying by 2 on the left and 5 on the right, am I still going to be dealing with the left-hand side being smaller? Think about it this way. This guy is tiny. And this is bigger. Right? So by multiplying these things on each side, now I have 2 times tiny and j plus 1, which is at least 5. Is this still true? 2 times a tiny thing is still smaller than 5 times a bigger thing, right? So the original statement still holds. It's an inequality. As long as I maintain the inequality, I'm good. But you see, I have to manipulate both pieces, right? I mean, I can, if I say, right? And I'm still true, right? As long as 2 is smaller than 5, and we're not dealing with negative numbers or anything like that, then I'm still going to be keeping the inequality. Inequality rules are a little bit weirder, you know? And I'll just put in a little verbiage. And now I'm going to steal from myself, if that's okay. Some of these statements have been like thoroughly ingrained in my head after doing this 100,000 times. And we didn't use I, we used J. Oh, sorry, N. Oh, and since we had a case, J was as far up the ladder as we climbed, and that was the assumption we made. But what we wanted to say is that it was true for any integer, which was the ultimate goal. So you climb somewhere up the ladder, and you're like, how am I going to get, I mean, can I really climb all the way to the top? And you say to yourself, you know what? I've gotten this far, and I can still climb. I can take that next step. So that means I can continue all the way up the tree, all the way up the ladder. Let's try another one. Okay, this is a good one. Plus 2 is divisible by 3. Positive integers. So let's convince ourselves for a second that it's true. If n is 1, is it true? So the base case holds. Oh, yeah.
To give some kids that's to hang up, and then that's more applications if anybody else wants to join.
Okay.
So some of those are page up on some pages.
Okay, I've got names. Okay, cool. Gotcha. No problem. Plug in 2 and see what happens. I mean, you know, see if it's really true. Convince yourself that it's true. If you don't believe it, then when n is 2, 49 plus 2, 51, and 51 is divisible by 3, right? Okay. So now you don't have to write it, I guess, but you just need to have it. But for my, oh, absolutely, I'm cheating. Why do you think I know them so well? Because I've printed them so many times. You don't know how many times I've done induction. It's disgusting. So the case, what is the n plus 1 case, the j plus 1 case going to be? What does it look like? Yep. There is a mathematical form to show divisibility by 3. You can say that 7 to the j plus 1 plus 2 is equal to 3 times some integer. But we don't need to fool with that. We'll deal with divisibility maybe later. I'm not sure if it's even in the curriculum. So we start with the assumption. So we could. All right. If it's divisible by 3, I might as well talk about divisibility. For some integer k. Because that's what it's saying. I don't care what k is. All I know is that it's some number that's an integer. So for example, I can say that 10 is divisible by 5 because there is a number out there, whatever it is, I don't care what it is, that when I multiply it by 5, I get 10. And in fact, I could say, well, I can't. I can't say that. So now how am I going to get this to look better? Okay, if I multiply it by 7, I'm gonna have to do some other things to it. So now I get 7 to the j plus 1 plus 14. But that's not really what I wanted, was it? How do I get it to look the way I really want it to look? I mean, what can I do to this to keep going? Because what I really want is the thing at the top of the page. How do I turn that bottom line into that top line? Well, I don't want all of the 14 off to the other side. I want how? Yeah, that would put me back where I started. I don't want all of the 14 there. I only want a little bit of the 14. How do you mean? Oh, just move that 7 over. The problem is that that would be division, and I would take it away from my first term too. I don't want all of the 14. I only want some of the 14. Okay. How much? Subtract 12. Yeah. Hmm? Well, let's see. I got my left-hand side the way I want it to look. Now what I need to show is that this right-hand side is something times 3. Right? And this 7k plus 4, is that an integer? Yeah, if I multiply an integer by 7, I still have an integer, and if I subtract 4 from it, I still have an integer. So this is still an integer. If I added a rational to it, or if I added 1 over an integer, something of that form. and m is just some integer. All I care about is that it's an integer. These are dummy variables. It's a dummy variable. It's there to hold a place. It's there to say I'm still dealing with an integer. Whatever the heck m is, I really don't care. And now we plagiarize ourselves. So a lot of this is so you have something to start with. You need to figure out a way to get to where you want to be. Yes. It's not a limit. J isn't a limit. J is some rung in the ladder. Right. Yeah, I'm trying to see if I can continue to walk after that step. Okay. All right. You ever seen the movie Indiana Jones and the Last Crusade? Ever seen that? Where he's standing on the edge of the cliff, and he holds his he's holding onto his heart theoretically, and steps out and lands, and actually lands on solid ground. He's stepping out. You remember that scene? Okay. Because he took that first step, because he is able to step, he knows that he can continue to walk. You see? Because he didn't fall to his death on the very first step, and he is able to make further steps, he knows that he can walk all the way across the bridge. Third one. Yeah, before they really screwed it up with the fourth one.
Yeah, okay.
Right, yeah. Yeah.
Oh, for like, for this one, it would be like something that
Oh. Huh? Well, it's true for all positive integers now. It's true for all n now. The other time it was true for all n as long as you were bigger than 4. Or that's part of the statement. That's saying that the statement is true for all. Yeah. Absolutely. Mm-hmm. Let's try this one. Yes. This? Okay. All right, try this one on your own. All right, let's dive into it. Yeah. Yeah. You want it to be divisible by 4, right? Well, that and that, first of all, if you multiply that out and then factor out the 4, you get something that is an integer. So base case. So 5 to the 0th plus 3 is divisible by 4. So I don't want to use J. Actually, you were trying to prove it for everything including 0. You want to. You want to prove it for what it wants, because sometimes the base case fails. And if the base case fails, then we're stopped right away. Well, you basically say false. It's not true at that point. So the base case holds. And now we're going to do 5 to the j plus 1 plus 3 is equal to 4k. K is an element of the integers. So we begin with the assumption. And the assumption was 5j plus 3 was 4k. Now we got to turn it into the other one, the upper term. So we multiply by 5. Minus 12, thank you. And we're done. We good?
Yep.
Fantastic. Let's see if we have time for one more. Yeah. Sure. Yeah. Just got to make sure that you're keeping the right bounds. Right. All right. Try this one. Still have a little bit of time. Ooh, this one includes rabbits. Rabbits are fun. So, do the base case. Show that it holds. So this just becomes and now we show that it's equal to the right-hand side. And okay, so the base case held. Now I'm going to skip some verbiage for the sake of time, because I know you are too. So the base case holds. Yeah, that's me being really, really brief. Don't you dare write that on your paper, and certainly not on the test. Okay. So the form we want, and this is worth actually doing, of 2 to the j plus 1 minus 1. Okay, so that's the j plus 1 case on the left. Okay. Yeah, because I want to get through this example before the bell. Plus 1. Minus 1. Okay, so that's what we're looking for. Now, my advice to you is on the side, figure out what the heck that ugly thing actually looks like. Simplify it, clean it up, because you're not going to land on that. You're going to get to that. Right? Oh. Hey, come on now. I've seen people write all sorts of weird things. My fault. Now, keep going. To do this, we begin with the assumption. Hey, I'm trying to get through this. And now we got to figure out how to get to the next piece. So, now, if we go up here for a second and take a look at this, this that's inside the summation becomes 2j plus 2 minus 1, which is 2j plus 1, right? That's what's inside the parentheses, right? If we distribute the 2, right? Distribute the 2 and then combine like terms. Come on now. It is in the morning. So what I need is to turn that into this. Sorry, this into that. Okay? Agreed? All right. We're not going to have enough time for this, but Isabel's going to ring in about 30 seconds. But, sure, take this as the first problem of your homework. I will put this on the next homework assignment. Hmm? Yeah, you're gonna have more than one problem for homework.
Are they all going to be solutions?
Who knows? All sorts of stuff.
It's doing this like those things that we were playing with.
All right. And I'll do this. The remainder is left for the reader. Yes.
Do you want us to copy this and break down our homework, or do you just want to look at it?
This episode of the Ronco Show has been brought to you by the Principle of Mathematical Induction.